To the final day of our FDP on emerging issues and challenges in AI and communication. Today we have Dr. Shyam Rajput sir from National Institute of Technology, Patna, and he's going to deliver his lecture on application of image processing in surveillance system. So before we start, I would like to read his bio. Dr. Shyam Rajput sir received his BE in Computer Science and Engineering from RGVP Bhopal, Madhya Pradesh in 2011. His MTech and PhD were from the Computer Science and Engineering Department from Atal Bihari Vajpayee Indian Institute of Information Technology and Management, Gwalior, in 2013 and 19, respectively. He has more than 9 years of experience teaching undergraduate and postgraduate classes. His current research interest includes artificial intelligence, machine learning, and their application in image processing and computer vision. He has published more than 50 journal and conference papers in image processing, computer vision, biometrics, and information security domain. He is currently quite active in the field of AI and machine learning. We have to move it. So as I was saying, he is currently quite active in the field of AI and machine learning. As a result, in recent years, he has published many very good quality works in reputed journals like IEEE Transaction on Instrumentation and Measurement, IEEE Transaction on Consumer Electronics, IEEE Transactions on Biometrics, Behavior and Identity Science, Expert System and Application, Information Sciences, Elsevier Signal Processing, Pattern Recognition Letters, and many more. Dr. Rajput has also edited 4 books in the domain of AI and machine learning oriented information security, multimedia processing, and computer vision.
नहीं अब वो तो छोड़िए, हम तो देखते हो EG1 में नहीं, हम EG8 में घुसेंगे नहीं.
Yeah. Dr. Rajput has also been granted 4 Indian patents related to field of AI-based image processing and computer vision. Based on his recent and active involvement in research, he has been also recognized in the world ranking of top 2% scientists in the area of artificial intelligence and image processing in 2024, according to a survey conducted by Stanford University, California. So without wasting time, let's hear what Dr. Rajput has to offer. Over to you, sir.
Okay, thank you, Mr. Naveen, for this nice introduction. And good morning, all the participants. So before starting, I would like to thank Mr. Naveen and other organizers of this faculty development program for giving me opportunity to discuss my research with the participants and inviting me here. So let me share my presentation. So hope this my screen is visual to all. Yes, am I audible, Mr. Naveen?
Yes, sir. Your screen is also visible.
Okay, thank you. So the topic for today's talk is image processing techniques for surveillance applications. So as the focus of this talk is on surveillance application, so most important and useful technique for surveillance problem is super resolution. So in this talk, we are going to discuss what is super resolution, need of super resolution technique. Then we will discuss some state of the art super resolution technique. We will start from the very basic and fundamental and first state of the art technique which is developed for the super resolution. Then we discuss some algorithm, some state of the algorithm that is developed by our research group. Finally, we will conclude and we will give some future direction that we will take away by our participant to start working in this domain and to develop the new models for solving this problem. So we are going to start with what is super resolution. So before discussing what is super resolution, let's first understand the meaning of resolution. What is resolution? So resolution is nothing but the DPI, dot per inch, or you can say that in simple word, you can say that this is the density of pixels per unit area. As you can see from this images, this example, Suppose this is the 4 cross 4 inch cross 4 inch dimension area or display of an electronic device. And the two images which one is in the left hand side, one is in the right hand side, the quality of these two images is quite different. Why it is happening? It is happening because here we have less pixels which we are spreading in this same area which we are here, like that is the 4 cross 4. So here we have a less pixel which we are spreading in this area. Here we have a large amount of pixels which we are spreading in the same size area. So because of the density of the pixel, this image is looking good. The information and features are very clear. Texture is also good, and we can easily detect what is available, what is present in this image. So that is the meaning of resolution. Means this image has a higher resolution as compared to the left hand side image. So resolution means the number of pixels in that particular area. So now comes to what is super resolution. So meaning of super resolution is this is the image processing technique that is used to recover or that is used to generate the higher resolution images from the low resolution images. So why this technique is required and how it is helpful in the present scenario and in our real life and real society. So let's try to understand the importance and need of the super resolution technique. So with the expansion of city surveillance systems and use of IoT-enabled devices like drone in law enforcement applications, and their role in resolving the criminal cases is also rapidly increasing. As we all know that in today's world or in today's days, 99% cases, 99% criminal cases are solved based on the CCTV footage and the images which are captured by the drone. What happened in the real scenario when the images captured by the CCTV camera and drone, they may not have a good quality because of the various reason. That one of the reason may be that image may be captured in the night, or there may be environmental factor. The suspect may be in the movement condition. The object may be very far from the camera, or low quality system. Government deploying the lot of camera in smart cities, but it is not affordable for the government to install high resolution camera at all places. So these are the some cases. These are the some reasons that make the criminal identification task based on these CCTV images challenging, because in all scenarios the CCTV footage are the images which are captured through the CCTV camera or drone, they may not have a good quality to identify the person from these images and videos. So let's try to understand this scenario from this example. So left top corner shows the Mehroli murder case, and these are the some the criminal cases that happen across the India. Like here, this is the Mehroli murder case where one person is shooting from one car to another through the pistol. And if you can see that this is the CCTV footage, but nothing is readable from this number plate. If this number plate can be read from these images, then we can easily solve this within a minute or within an hour. This kind of cases can be solved easily. Similar case here, one lady is trying to stealing some item from the mall. One person is stealing something from the go down, and these two are the kidnapping cases. One from Mumbai railway stations when one person has kidnapped one child, and here the criminal is trying to run away from the spot of the crime. So you can see that from these original images, it is very difficult to identify the criminal, who is that person or who is that lady. Because if we know, suppose this is the one example, if we know her, then based on the, if we already know her, then we can say that who is this lady, why, based on the gesture and posture. And if we don't know the person in advance, then it is very difficult to say that who is this, why watching, why seeing their faces, because nothing is readable, nothing is visualized from these kind of images. So these kind of scenarios make the surveillance task challenging. Similarly, you can see here by this face, we cannot identify who is this person. Even the human as well as even the system will also not be able to identify the person. And the existing algorithm may suffer to extract the features from these kind of images, because completely it is black, texture is not there, and individual identity information is not visible in this kind of images. Similar kind of images we have also seen during the COVID period, where different state government trying to enforce the lockdown at the different locations. And at that time, drone images were using to identify the criminal activities or to identifying the suspect. But as we know, the drone fly at very high speed, and sometimes the captured images are not quite good. So identifying the person or identifying the criminal from these kind of images are very challenging. So how we can solve this problem? So in the basically what is this problem? This is called the low resolution problem. Research community consider this problem as a low resolution problem, and it is known as a low resolution problem in the literature research papers. And how we can solve this problem? First of all, we have understand that this problem must be solved, because it is not useful. The images captured from these kind of low quality images are not useful in any applications. So this problem must be solved. So the solution to this problem is a super resolution technique. The super resolution techniques are capable to generate the high quality images from the low quality images. The task of super resolution technique is not to increase the resolution. Apart from this technique should be simultaneously reduce or remove all kind of artifacts from the input images, like noise, blur. If there is a low light effect, then super resolution techniques should also remove that low light effect from the images. So now we are going to discuss the what are the different classes of the super resolution techniques. So super resolution techniques may be of generic image super resolution technique and domain specific image super resolution technique. Generic image super resolution techniques can handle any kind of images. Any type of input image can be passed to the generic image super resolution technique, and they will produce the uh, high resolution version. While the domain is specific SR technique like face SR, text SR, iris SR, fingerprint SR, they are specifically designed for the domain specific images. Purpose is that in the applications like face recognition, biometric, not only the resolution is important. Apart from the resolution, their individual personal characteristic is also important for their unique identification or unique verification. So for that purpose, for domain specific images like faces, text, iris, and fingerprint, these kind of images are used in the recognition as well in the biometric applications. So for these applications, there is a separate class of super resolution technique, which is called domain specific SR technique. So as the focus of this presentation is on only the face images, because we are going to discuss the surveillance applications, and in the surveillance application, most of the time facial images are used to identify the criminals. So face SR techniques are further divided into the reconstruction based and dictionary based SR techniques. Reconstruction based SR techniques are those techniques which work on the single input image only. We do not take advantage of any dictionary images or any data set images. They are capable to reconstruct the images. They learn the feature from the same input images and try to generate their high resolution version. But these kind techniques are not much capable or not much good enough to generate the high resolution images. Only few papers are available at the beginning of and around 2001 or two paper came on this topic only. After that, the researcher used or started working with a dictionary based SR techniques. So in the dictionary based SR technique, this may be the machine learning based and non-machine learning based both. In these techniques, model use some dictionary images or dataset images to learn the features and to generate the high resolution version of the input test images. So these dictionary based data technique can also be further divided into local patch based and global phase based. Local patch based in the local patch based techniques, images are divided or split into the patches and each patch processed individually. Once we process all the patches, then merge all the resultant patches to form the complete phase. While in the global phase SR techniques, complete phase is executed or processed in single run. So local patch based SR technique may be the neighbor patch based and position patch based. So apart from these out of these all techniques, only the position patch based SR technique, which may be machine learning based or non-machine learning based, is the most prominent and has been proved to generate the better result as compared to the other techniques. So because of this reason, in the coming slide, we are focusing only on the position patch based super resolution technique. So let's try to understand one fundamental concept of position based patch based super resolution technique. And this concept given by Ma et al. In 2010, and this paper was published in elsewhere pattern recognition. So what this paper says that if two LR patches are same, basically this model work with the one assumption that if two LR patches are same like this one, then their corresponding HR patches will also same. This is the one thing. Now, how this position patch based model work? Let's try to understand. So in this model, these basically, first of all, we are discussing all models we are discussing. These are all the non-machine learning based model. These are purely the statistical model. So two things we already have. We have a input test phases in advance, and we have a dictionary images. So in the dictionary image or data set, this is called dictionary or data set. I will use these two terms repetitively. So in the dictionary, contains the LR and HR pair. Okay. So for each LR pair, there is a corresponding HR image also. For each LR image, there is a corresponding HR image. So this kind of images we have in advance. Input image we already have, that is the test image. And our task is to generate this high resolution output image. So how does it take place? As this is the patch based method and position patch based method. So first of all, we split the image into the patches and we process each patch individually. So what we do, we represent this one input patch as a weighted linear combinations of same position patches from the dictionary. Same position LR patches from the dictionary. Suppose let's assume this is the Y patch, Y value, and this is, let's assume this is the X1, this is the X2, and this is the X3. Or you can say this is the Xn. So what we do, we try to apply some coefficient with this X1, X2, and X3 or Xn, and we add these all terms to get the value Y. This is the meaning of weighted linear representation. We associate some weight with each individual LR patch, same position patch, and we try to represent this Y with the combination of these values. And this representation may not be accurate, may not be perfectly matched. Okay, so I'm not using this. Using equal sign is not correct. This may be approximately equivalent, not equivalent, approximately equivalent. So what is the meaning of approximately equivalent? So let's assume the value of Y is 10, and with all different combinations we are getting 9. All different combinations we are getting 9.9. Not exactly, we are not unable to exactly represent the test patch with the different combinations or dictionary patches. There may be some error. So this error is a 0.1 error. So this error is called the representation error. And this error should be as minimum as possible to getting the best value or best outcome. So how we can reduce this value? By driving the optimal values of these W1, W2, W3. So that is the target, that is the objective of this problem. We try to generate the optimal weight in order to reduce this representation error or this reconstruction error. Once we have this weight, okay, as this work with the assumption that if LR patches are similar, then their corresponding HR patches are also similar. We apply the same weight to the, multiply the same weight with the same position HR patches. Okay, same position HR patches, like this is W1, X1, W2, X2, W3, X3. Sum all these component, then we will get one output HR patch. And we apply this process for in the raster scan order from top left to bottom right. So after each operation, we have a one patch. Finally, we merge all the patches to form the complete HR image. So how this process mathematically represent? This process is mathematically represent like this. This is the input phase. This is the dictionary LR phases, and each phase is associated with the weight, sum of all them, summation of all product, and there might be an reconstruction error. Task is to reduce this reconstruction error. How we can reduce? By getting the optimal values of this weight. So to achieve this, this simple expression is converted into the minimization function. Here, this minimization function. So this component, this whole component is shifted to this direction. So this is Fi. This Fi UV minus this part, this term, and this is equivalent to eta. And task is to minimize this eta. How we can minimize? By driving the, by optimizing, by tuning this weight. So this is now, this becomes the minimization function. So we can use a statistical approach to minimize this function. We can also try some soft computing algorithm to minimize this function, because minimization and maximization is a common problem in the soft computing. We can apply the soft computing problem to minimize this function, or we can also go for the machine learning approaches. So this is the work, first state of the artwork for image super resolution, face image super resolution task, published in 2010 by Ma et al. So problem is, this is the good, this model work well when images are free from any artifact. If images are corrupted by the Gaussian noise, that is most obvious in the, practical scenario. So when images will be corrupted by the Gaussian noise, that time this eta term, this error term become more wider. And in the presence of noise, we will not be get optimal weight because of the wider range of eta. We will not be able to minimize this. We can minimize, but not at optimal level. So to overcome this problem, next paper that is published, I will come back to this part also. Next paper that is published in 2014 by Jiang et al. In the IEEE transaction on multimedia. So what they did, apart from this term, they added one more term in the objective function. So what is the meaning of this term? This is called the regularization term, and this is called the fitting term. So with the weight, they associate one matrix, and this is the diagonal matrix, which is keeping the information of distance between the input patch and the dictionary patches. And 1 upon distance is used in that matrix at the diagonal element. So if distance is higher, means the patches which are less similar to the input patch, we will give, means this model should give less weight to those patches which are dissimilar or very less similar to the input patches. And those patches which are closely similar to the input patch, they must get the higher weightage. So this is basically trying to give the more weightage to those similar, more weightage to those patches which are similar to or close to the input patches. So this concept is called locality regularization, and it helps the model in handling the noises kind Gaussian noise. This concept make the super resolution task robust to the Gaussian noise. So again, after this optimization, finally we get the weights, and these weights are multiplied in all models. Same rest process is same. Then weights are multiplied with the high resolution counterpart of the dictionary images to get the final resultant output patch. Here UV notations are denoting one patch. F denoting phase, W denoting weights, FR denoting the resultant phase, and UV associated with these all is representing the patch. So this regularization term make the super resolution process robust to simple kind of noise like Gaussian noise. And in practical scenario, it is not necessary that image will always be corrupted by the Gaussian noise. In practical scenario, our images may be corrupted by other kind of noise like impulse noise, mixture of Gaussian and impulse. So to make the model or super resolution task robust to the mixture of Gaussian and impulse noise, we first introduce one paper that published in 2018, and this was the first paper for mixture noises. And what we did in this paper, instead of using this test image directly in the weight calculation process, we first created one guided phrase from the dictionary images, and we compared this image with this guided phrase with the text phrase. Okay, and if the pixel value in the guided phase and the difference of the pixel value with the guided phase and the test phase is greater than some threshold, then we are detecting those pixels as a noisy pixels, and we are excluding those pixels from the computation. So how does it take place? Let's see this algorithm. So what we are doing, first of all, we are creating one guided phase from the LR dictionary images. Okay, this L part is representing the low resolution LR dictionary phases. And we are comparing the each pixel, ij is an individual pixel. We are comparing each pixels of the test phase with the guided phase. If this difference is greater than the threshold, some threshold, that is the tunable parameter that has been tuned experimentally. If this difference is greater than threshold, what does it mean? Means the pixel has been corrupted or destroyed by the noise. So in that scenario, we are replacing that pixel value with the guided phase pixel. We are not going to process the original noisy pixel in the objective function. We are replacing those all pixels which has been identified as a noise by the guided phase pixels. If the threshold is less than, if the difference is less than the threshold, we are going with the same information. Means this. Okay. So if the pixels are being detected as a noise, see, we are replacing those all pixels with the guided phase information. If otherwise, we are going with the same information, which is available in the original LR test images. So in our objective function, we are not passing here direct input images. We are applying some algorithm, thresholding weight algorithm to replace. First of all, we are detecting the noisy pixels, then we are replacing the pixels, then we are computing the weights. So this is the one small difference, and this idea published in the signal processing in general. Now the drawback of this problem is that let's first see, this is the pseudocode of the complete algorithm. We have a test images, training and test images, and these are some tunable parameters that we have to fix experimentally, like some parameter we have to fix at the starting, like what is the image size, what is the overlap, what is the patch size, and this is the pseudocode of the algorithm which we have discussed here through the diagram. So before discussing the drawback of this particular algorithm, let's see what are the possible metrics in this domain. So the common performance metric which is used in this domain is the PSNR and SSIM. What is PSNR? PSNR is the peak signal to noise ratio. And first of all, we compute the mean square error. First compute we mean square error. Mean square error between the this our one is our generated image, output generated image through the model, and one is the ground truth image. So first of all, we compute the mean square error between the output result and the ground truth images, and then we use 10 log 10 255 square upon MSE, mean square error, as its name peak signal. So for images, the peak signal is a 255. So 255 square upon MSE. So this is the meaning of peak signal to noise ratio. This is the noise that is being detected by mean square error, and peak signal is a 255. In the case of images, as I told, peak signal value is always 255. And next important matrix. This matrix is helpful in detecting the presence of noise in the images. And for the images like face, their structure is also important. Their individual characteristic also important. So the second important matrix that is used in this domain is the SSIM, structured similarity index. And this is the formula. Here mu x, mu y are the mean, standard deviation. Okay, so this is the formula for SSIM. So two things, these are the two common standard performance metrics that are used in this domain for measuring the performance of any developed model. So this model and this with a small idea of replacing the noisy pixels by the guided face information, we are able to get good performance as compared to the recent state-of-the-art work. Now, these are the visual results, but I am feeling that through this online presentation, you might not be able to analyze what is the improvement of the existing over, what is the improvement of the proposed over the existing work. So, as the algorithm have many tunable parameters like lambda, that is the regularization term, k number of, these are the parameters which is used in the objective function. Yeah, this k, this lambda. So these are all the tunable parameters that we need to tune experimentally, and we are reporting here the values of those parameters. So it says that instead of all images, there is only need to consider 50 to 40 images in order to get the good performance. Now, what is the drawback of this algorithm? What we are doing, we are extracting the, we are detecting the noisy content, then we are replacing those content from the guided face information. Let's think about the scenario. Suppose 50 to 60% pixels has been detected noisy, then we will replace those all 50 to 60% pixels from the guided information. So what we are doing, we are losing the personal characteristic. But for applications like biometric face recognition, personal information is much more important, or you can say that more important than their visual quality, visualization or visual representation. Personal information is more important than their visual representation. So with keeping this thought in our mind, we came up with another idea. So what we did, we are not going here to replace the information. What we first try to understand the first try to detect that whether the pixels are being decreasing or increasing by the noise. What noise does? Noise either decrease the pixel value or increase the pixel value. So we are trying to give the different treatment to those pixels which has been decreased and different treatment to those pixels which has been increased. So we are computing two vector. One is the vector VL, second vector is a VH. We are not going to pass any, we are not going to replace any original content in the input image from the guided image. We are first computing two vector that keeping the information of whether the pixel value has been increased or decreased. Once we know these two vectors, once we detect these two vectors, we are trying to tune them, we are trying to multiplying them with some constant value to make them or to reach them to the original value, which has been corrupted, that is unknown. That's why this is a challenging task. If we suppose we know that original, suppose we had this information, suppose original pixel value was 45, now it has been corrupt due to the noise, it becomes 30. And suppose if anyhow we make this 45, then our task will be solved. But this has been corrupted, this we don't know in the test images. So we know that the information has been decreased, that maybe by 15 or by 14 or by 13. We can detect this kind of information. Now we try to multiply some factor in this to reach them to 45 or near to 45. If we will get the 45, then this problem will be completely solved. So to achieve this, what we did, we first thing is that we are using the original images here only. We are not replacing any pixel. To task is to preserve the personal information in the resultant images, and whatever vector we are getting, we are multiplying with two tunable parameter. So VL, as this is the vector which has been decreased, so we want to increase this value, and those as already been increased by the noise, we need to decrease those values. So VH is considered as a negative, included as a negative in the objective function, and VL is included as a positive in the objective function, because we need to increase this and we need to decrease this. And how much we need to increase, how much we need to decrease, that we don't know, because the original information has been lost due to the noise. So that we don't know. So that's why we are using the tunable parameter. We are trying to reach near to that point. So this again, this is the small concept, a small idea what this allowed to get, this allowed us to get the good result, and this paper has been published in the IEEE transaction on biometric behavior and identity science. The purpose of discussing this is that I think you can understand that small concept may give you a good performance, and we can get the good publication with these small concepts. That's why I'm not going to discuss here. I'm not discussing any higher level models. I'm discussing only those things which are very basic. You can think how we can do the small changes, how we can first of all, we must understand the problem very closely. Then only we can do these small changes, small contribution we can do to get the good publication or good outcome. Now, this is the overall working, how we are computing the VL and VH. And this was the previous model, ESNR. Where we were replacing the pixel value of original image from the guided phase, and this is the model where we are computing two vector VL and VH. And you can say that this second model is achieving better performance in terms of PSNR and SSIM as compared to the previous model. Now another thing is that suppose we have this kind of image. Suppose we have this kind of image, and we want to completely resolve the noises because nothing is visible in this image. So neither human nor machine can detect anything, nor neither human nor machine can identify the person who is the person in this picture. So one more model we have developed to which is able to generate this or able to produce this kind of images from this. and very small concept is working behind this only. So what we did, first of all, actually this is the, as you can see from this picture, what kind of noise is present in this. This is the noise which is here is a impulse kind of noise. You can analyze from this picture only. Some pixels are very white, some pixels are very black. So this is the salt and pepper kind of noise or random noise. What this is the impulse noise. Impulsive nature is there. So in all these methods, our task is to compute the difference between the dictionary pixel and the input pixel. So suppose we have a A1, A2, A3 like pixels here, and B1, B2, B3. These pixels are from the dictionary. This pixel is from the test image. And our generally we are doing the L2 norm. In all functions, we have this L2 norm. That is this L2 means the square Euclidean. Sorry, this is the Euclidean distance. This is the square of the Euclidean distance. So if this pixel is corrupted, suppose this pixel is corrupted. So if we exclude this if we exclude this part from the Euclidean distance calculation, then there will be negligible effect on the distance measuring. What we do in the Euclidean distance, we do A1 minus B1 square plus A2 minus B2 square plus A3 minus B3 square. And if we remove this component, suppose we have detected that this is the outlier or this pixel has been corrupted by the noise. If we remove this information from this Euclidean distance, then there will be a negligible impact on the calculation. So with this idea, what we did, we first identify the outliers from the images because most of them are the outlier. So we first detect the outlier from the images through the existing outlier detection technique, and we exclude those outlier from the computation. That is only the simple idea, and this paper was published in more than 8 impact factor journal of elsewhere. So what we do, we first find out the idea. We first compute the outlier vector using the existing outlier detection technique. OUV is the outlier vector, keeping 1 if the pixel is not detected as an outlier, and keeping 0 information if the pixel is detected as an outlier. And we multiplying, this is the dot product, we multiplying with this information. This is just a representation that we are removing the outlier pixels from the computation. Means 0 and 0 will be multiplied here, it will make the distance 0, and 1 will be multiplied means it will keep the same information which is over here. Okay, so this is the thing which we did in this work. And addition to this, we have included one more fidelity term. So we are applying the iteration over iteration. So after each iteration, we have a one HR input images, HR resultant image. We want to further improve that. So we are applying iteration by iteration over this. In all previous models, there is only one iteration. Now we are applying the iteration concept over here to further improve the resultant HR images. So this model is able to get the good performance as compared to all other previous models. These all are, most of them are the transaction paper only. And one thing you can see from here that we have considered two type of impulse noise. One is salt and pepper. Second one is RVIN, random value impulse noise. So in this salt and pepper noise, this is the result is very standard. While in the case of random value impulse noise, you can say that when the noise percentage 50% in the salt and pepper and random value, here we have performance 30, and here we have only 23.12 PSNR value. This is the PSNR value, and second row is the SSIM value. So what we can take away from this result, we can take away that in the case of RVI, still we have a lot of scope to improve the performance of this model, because the detection of our random value impulse noise is quite difficult as compared to the salt and pepper noise. Salt and pepper noise produce the random value, corrupt the images at the random locations by either value 255 and 0. So it is easy to detect. What the nature of random value is different from the salt and pepper. It in this location is also random, as well as value is also random in the range of 0 to 255. So this random nature is very difficult to complete detect, very difficult in its complete detection. So that's why there is still scope for further improvement of this model, because there is a huge difference in PSNR value with the same noise level. So another problem we resolve in the practical scenario or in real scenario, suspect may be in movement. So that causes the motion blur in the test images. So what motion blur does, it shift the pixel value with some angle or with some length in the same images. So what happened actually, due to the movement, due to the motion blur, some value, suppose some important information is originally should be here, but it now not here, it has been moved either here or here with some length or angle. So this is the motion blur. So to solve this problem, in all model, what we do the position patch concept only. For this calculation, we will consider this position patch. But due to the movement, the information may not be accurate at the same position. This may be shifted with here, this may be shifted with here, this may be shifted with here or with here because of the motion. Okay, so useful information may we get in the next nearby or neighboring patches, not the same position patches. So to resolve this problem, to resolve the or to make the super resolution model robust to the motion blur, we use the concept of proximate patches, not the position patch. So what is proximate patches? Instead of considering the same position patch, we are also considering surrounding patches also, because the required information may also be here due to the movement or due to the motion. So in the position patch methods, we consider only one patch, same position patch. What as due to the motion effect, the required information may be available in the surrounding patches. So these are called the proximate patches. So we are considering 25 proximate patches in the calculation. So it helps in retrieving the information from the surrounding patches, because the original information is not available, as required information is not available at the same position due to the motion blur. And this is represented here. So this window is saying that not only the same position, we are also considering surrounding patches, that is called the position patches. So here the vector size is much larger as compared to the position patches, because 25 patches we are extracting from one image, and suppose 360 images are there, so size of the vector is much higher, number of weights are also larger in this scenario. So what this idea make the this idea considering of the proximate patches instead of the position patches make this process robust to the motion blur. Apart from this, we have some more contributions in the coefficient calculation process also. So this is again published in IEEE transaction. Now, all the method which we have discussed so far, they are all only the statistical approaches. We are applying some concept in the objective functions only to make the process robust to noises. Now, due to the very spread use of or very frequent use of the machine learning algorithm in this domain, we also motivated with the advancement of the machine learning. So to make the LR process, we developed one machine learning algorithm, that is the regression learning based model. And what this model does, it directly try to extract the, try to estimate the noise level, how much noise is present in the images. Once we know that noise level, then we can exclude that noise level from the training images. So we train the Gaussian process regression model and 4 feature we have used from the noisy images, noisy training images: mean, variance, entropy, and homogeneity. We learn the model, we train the model on these 5 parameters. 4 are the feature, and 5th one is the corresponding noise level. We have already corrupted the noise training images with different level of noise. We train the model learn that if with these features and corresponding mapping of the noise. Once we train the model, we use the train model to pass to test or to detect the or to predict the noise level from any random test images. So the advantage of this model is that it predicts the noise level. Once we know the noise level, we can exclude this noise level from the objective functions and from the objective functions to make the process robust to the noise. It is similarly that suppose we are fighting with some strong person. So one thing is that either we can make ourselves stronger or we can make front person weaker. So once we detect the noise or once we detect that power, we can incorporate that power in ourselves to make ourselves compatible with front person. Okay, so because the test images are noisy, once we know the noise, we import same noise level in the training images to make the training LR images consistent with the test image.
First of all, I would like to you all that you are really the partners for us and being the part of the Bank of Baroda. Before starting the session, I would like to elaborate more about the Bank of Baroda.
Yes.
We are the second.
Sorry for the interruption.
No issue. I think one more event is also going. Okay, so thing is that as time is very limited, so let's understand what is the overall limitations of all the models which we have discussed so far. So the limitation is that they are only suitable for the frontal images because we are using the concept of position patch or proximate patches. This concept will work only when we have a frontal images. Okay, then only we can assign different weight. We can think about the weighted linear representation. If images are not frontal, then we cannot think about the weighted linear representation. This is the biggest drawback of all the model which we have discussed so far. Another drawback is that the model are means different author along with us. We have tried to make the super resolution process robust to different kind of noises. What these models are unable to handle the occlusion. Suppose there is a black spot, then we cannot handle, we cannot process that black spot because all the pixels become, there will be a 0. So we cannot compute any weight for the 0 value. So that is the another drawback of these all models which we have discussed so far. So to overcome this problem, recently in recent 4-5 years, deep learning based models are also getting prominence. And these are some result of the deep learning based model. You can see that these models are able to handle the non-frontal images. These all are the non-frontal images, and they are also able to handle they are also able to reconstruct some sunglasses. That is a kind of occlusion only. So this is the advantage of the deep learning based model. So by motivating from the recent advancement of the machine learning or deep learning in the field of image super resolution, we have also developed one deep learning based super resolution model, and this work is published in the one of the IEEE transaction. So what we did in this, we first design one coarse SR network, which take the input LR images and generate the one intermediate high resolution images. Then we applying some hybrid feature attention unit, attention in attention unit to extract different kind of feature, less important feature, more important feature, to build a one model that is the SR model that generate the super resolution image. And then we use the discriminator to check whether that image is appropriate or not. If not, then again we train the model further and further. So we cannot further explore, we cannot go in detail of each block. Of course, it will take more than 1 hour to discuss this kind of model in detail. But here we are, I can give the brief overview. We are using the convolutional and deconvolutional layer in order to generate the coarse SR network, coarse SR image. Here, this is number is showing that what is the size of the filter, what is the number of filter. 3 cross 3 is the filter size of 128, and then 128. Here, stride is also mentioned. So these are the different parameters of convolutional layer and deconvolutional layer. And the thing which you can understand from here, that participant can understand that the deep learning model can also be applied for this problem, and they can look for the attention blocks. Different kind of combinations of different attention block can be applied in this domain in the problem, for the problem of a super resolution. So these are the result of our proposed model, this hybrid feature weight attention block model paper. So you can say the resultant images are very close. Second, what last column is the proposed model, and this one is the HR images, ground truth images. And we can see that, we can feel that, or you can easily visualize that the resultant images are almost similar to the ground truth images, are very close to the ground truth images. So now let's understand what is the difference between these two approaches. One is the deep learning approach, second one is a non-deep learning approach, for which approach we should proceed. Okay, so each approach have its own advantage and limitations. Like when we talk about the reconstruction capability, so no doubt in the reconstruction capability, deep learning approaches are more stronger as compared to the non-deep learning techniques. It has been proved that deep learning techniques are better in the reconstruction of the LR face images as compared to the non-deep learning technique. It is obvious also. Okay. Second thing is the computational complexity. So to train the deep learning based model, a lot of computational power is required. I think we all agree with this. And it is, as far as Indian scenario is concerned, we all cannot afford the supercomputer and high performing computer. So for those researchers who have a limited capabilities in their institute, or they self have a limited computational power laptop or desktop, how they will work, how they will do the research. So obviously we have to go for the non-deep learning techniques. And in recent years also, in spite of the prominence of the deep learning techniques, in recent years also many non-deep learning, purely statistical based technique, statistical technique based papers are also publishing in recent year. So it is not mandatory that we should focus on deep learning based techniques only. Thing is that because it is why non-deep learning based techniques are also important in present scenario. It is because of the third point, dependency on the training images. So to train the images, thousands, or for training of the deep learning images, more than 10,000 images are required. What it is not always possible. Suppose we have a one data set of 1 lakh images of Chinese faces. Suppose we have developed the algorithm, we have trained the model. Okay, and for the Chinese images, we have developed model and tested, and we got that best accuracy. When we apply the same model for in the scenario of our South Indian images, suppose we want to deploy the same model in the South in any surveillance system, then that time model will be fail. Why? Then because of the nature of the images. The Chinese faces is completely different. Structure of the Chinese faces, texture, color of Chinese faces completely different with our Indian faces. So for each kind of domain, it is very difficult to arrange the more than 10,000 or more than 1 lakh images Okay, suppose we have developed the model for our we have trained the model with Kashmiri, Jammu and Kashmir peoples, and we want to deploy in the south, then model become fail. So this is the again the challenging task. Gathering of the 1 lakh or 2 lakh or more than 50,000 images from the same domain people is very challenging task. So the advantage of non-deep learning based model is that they can work with the 50, 100 and 200 images. So these advantages of non-deep learning based technique make them more practical or more realistic in the real scenario. So each technique has some advantage and disadvantage. So let me conclude this session. So what we have discussed that current non-deep learning based models are unable to handle the artifacts like occlusion, we have already seen. These models are efficient only for frontal images because most of them use the concept of the position patch, which work only when images are frontal. No universal method available in the literature that can handle all kind of digital image noises, digital image processing noise, because one model is capable to handle only impulse noise, one is good for the Gaussian noise, but no universal method is right now available that is that can make the SR process, superposition process robust to all kind of noise. Another conclusion from this is that the deep learning based method can handle the non-frontal images, but output of non-frontal images are also non-frontal. We can see from here, if the images is non-frontal, then output is also non-frontal. Like what for the application like surveillance, biometric, frontal faces are more important in the human detection, criminal detection. So this is again the challenging task with the deep learning based methods also. So with this, I am defining two, or I am listing out here two future directions. One is the need to develop a model that can generate the frontal HR face images from non-frontal LR images. This is the current problem in the literature. And second is the developed model should also be robust to different image degradation factor. Means our model should be robust to all kind of noises, all kind of other artifacts like motion blur, low light, occlusion. So these are the two future directions that can be taken away by our participant if they want to work in this domain. These are the very recent problem, and that can be taken away as it is to develop the new model, to develop the new algorithm to solve this problem, super resolution problem, to make them more appropriate for application like surveillance. So these are the key references which we have used in this presentation. Thank you all for listening me. If you have any query, please ask.